Okay, hello, North Tahoe High physics and maybe calculus students. Today we're going to do deriving the kinematic equations using some basic calculus. The motions we're going to consider really is only one, and we'll do it completely, and we'll figure out constant velocity motion we can get if we understand uniformly accelerated motion. So let's just take a look at that one. So there are two pretty simple perspectives. Let's just take a look at what the meanings of these things are. Remember, calculus is just numerical techniques to do some pretty much ordinary things, finding slopes and finding areas. So if we have some position function, x as a position of t, then we must say in calculus that velocity is the time derivative, dx dt of v. And how are these little d's different from the deltas that we use in the algebra-based course? These are really, really small. So we're talking about a velocity that comes from a change in position over a very, very small time. So we're talking about, you know, the limit as the time approaches, or as the change in time approaches zero. And then conversely, or not conversely, but as a next step forward, dv dt equals acceleration. And I suppose sometimes you might see that as the second derivative of position versus time. So those are good to know, right? The slope of one gives you the value or information about the one underneath it. But how are we going to actually get the kinematic equations from this? I think it's easy to use the other technique of calculus, and that is taking integrals. So let's start that. So let's take a look at, I think the easiest place to start is actually with the acceleration. And you understand that we're going to study in this class just constant acceleration. So the acceleration won't vary. That means that we expect a flat line here when we're dealing with acceleration versus time. So a is constant. So I'm going to recast it this way. I'm going to say then that small change in velocity is equal to a times a small change in time, in the differential form. So if I integrate this, it will look like this. I'm going to do the integral of dv, and that should equal, if these two are equal, the integral should be equal to a times delta t. And I'm going to integrate this from vi to vf, and we'll integrate this one from t equals 0. So we'll just say we're going to start at time equals 0 to some time t. So the integral here, if I do this right, remember there's just, you can think of it's 1 dv, so the integral is just v, and from vf to vi, and we have in this case a is a constant, so the integral of this one is at, and we're evaluating it from 0 to some time t. So if we expand this out, we get xf minus, or vf rather, minus vi equals a t. And actually, you know, I'll do it just to be complete. This would be a t at 0. But since we're saying that's 0, it looks just simply like that. So that's our first kinematic equation. And sometimes you might see it look like this. Vf equals vi plus at. Okay? Okay, so let's do the next one. Let's take a look at v versus t. We just figured out from finding the integral of of the acceleration function that we have dx over dt, which equals v, and we said it equals this, vi plus at. So we're going to do the same thing. I'm going to multiply by dx on both sides, so I get a vi plus at dt, and integrate it. So take dx, the integral of, I'm going to do it as one integral, but you guys probably realize this would distribute through. You could do it as two. And our limits here will be your initial position and your final position, and we'll do time equals 0 again to some final time t. Okay, so we have the integral of that would just be x, evaluated from xi to xf. This integral will be v times t plus 1/2 at squared, and that's going to be evaluated from t and 0. So we clean this up a little bit down here at the bottom. xf minus xi equals v times t plus 1/2 a t squared. And again, sometimes you'll see it written this way: xf equals xi plus vt plus 1/2 at squared. So that's your second kinematic equation. It's an expression for position for something that's under constant acceleration. So those are really the only two equations that we can derive. We'll look at one more here in a moment, but we didn't do constant velocity, but we actually already have done it. Constant velocity would mean that there's no acceleration. So these are the equations for uniform acceleration. And if we said there was no acceleration, all the a terms would go to 0. So your constant velocity would just be these ones with a as 0. Vf, of course, it would just be Vi. So there's one more equation that's pretty often used in kinematics. It would be nice if we could have, since we've derived these two equations, and this is just a re-expression of that equation, it'd be nice if we could have one equation that doesn't involve time. What if we just have acceleration, position, and velocity functions? It turns out it's not hard to do. It's a lot of algebra and some order of operations, and it's really easy to lose a sign. But if you're interested, I could show you how to do it, but I'm just going to skip to the point. We could combine these two equations and come up with an equation that looks like this. The final velocity squared equals the initial velocity squared plus 2a times the displacement delta x. So that is our final, our third kinematic equation. So here's 1, here's 2, here's 3. Okay, guys, hope that helps, and we're going to practice working on this stuff tomorrow.